Hi everyone, today we're doing titration calculations. Now our syllabus outcome is still conduct practical investigations to analyze the concentration of an unknown acid or base by titration. So you guys have had a bit of a look at titrations in general, how to use a bit of the equipment, but now we actually have to get into the nitty gritty and actually do some of the calculations. So it's the revision parts. Acid plus base gives us salt plus water. Acid plus carbonate gives us salt, water, and carbon dioxide. Acid plus metal gives us salt plus hydrogen gas. Now these are very important, especially that first one. Acid plus base gives us salt and water. We need that for our titration calculations. Always remember that one. I'll be quizzing you, and if you don't remember, I'm going to throw you down the stairs. Now, concentration equals N over V, so number of moles over volume. Okay, so concentration in moles per liter is moles over volume. Now, titration calculations, they generally involve using concentration and volume to determine the number of moles of each reagent at the point where there is a stoichiometric quantity of each reagent, which means that we're looking for the point where there's equal amounts of both. If our reaction's 1-to-1, then there'll be 1-to-1 moles. We know this is known as the equivalence point, so it's where the number of moles of each reagent are equivalent. Okay, so it's our equivalence point. There's three main ways to determine the equivalence point. Okay, when we're doing a titration, we can use an indicator and we can watch for that sudden change in the indicator. Now we have to use specific indicators. We can't use universal because it's too it's not sharp like the individual indicators are. It's quite a broad indicator. But we're wanting a very sharp change. Okay, so something like phenolphthalein goes colorless to pink. Okay, remember from our lesson a few weeks ago, indicators. Phenolphthalein goes colorless to pink, or bromothionol blue goes yellow to blue. It's a very sharp change. We can also use a pH probe, and we can follow the pH of the titration as we go, graph it and calculate the equivalence point using that. Or we can use solution conductivity, where we measure the conductivity. Now with the solution conductivity, we're measuring the amount of electricity that the solution conducts. Now there's very specific ways to tell the equivalence point with that, which we'll go through in a future lesson. But each of them is a valid method of finding that equivalence point. Okay. Each titration run is known as a titer, and it's the volume that is read off the burette. Okay. More specifically, it's the volume difference that's measured off the burette. We don't always have to start the burette at 0. We can start it at 0, 1, 1.1, 10, whatever. As long as the endpoint comes before we run out of measurement, okay, as long as it's less than the 50 or 100, whatever volume of burette you're using. All of ours are pretty much 50. That's the most common one. And so that's our titer value. It's that volume change of the burette. Okay, so it's basically final takeaway initial. The other reagent delivered into the reaction vessel with a known quantity, okay, and that known quantity is whatever the volumetric pipette is that we use. So typically we use a 25 ml volumetric pipette. Depending on the concentrations and the type of reagents, sometimes you might have to use a 10 or a 50 or 100, but take note of what volume you're actually using, and it will tell you in the question. Now, the concentration of one of the reagents will be accurately known before doing the titration, whether that's from primary standard, secondary standard, or whatever. We will be able to get that information generally to 4 significant figures, if not more. Now, from this information, the concentration of the second can be calculated. How do we do it? So let's have a look at an example. So to determine the concentration of a sample of sodium hydroxide, it was titrated against 25 ml samples of 0.1059 mole per liter hydrochloric acid. The burette readings are shown below. What is the concentration of the sodium hydroxide? In a HSC, it would probably be calculate the concentration of the sodium hydroxide solution. Okay, just remember your HSC verbs there. So what we've got here, we've got 4 trials, and we've got those initial and final burette readings. Now, to find the titer value, so the actual volume delivered during the titration, we do the final reading, take away the initial reading, okay? So for the first one, it'd be 24.55, take away 0, which is nice and easy. But then the next one's 48.65, take away 24.55, so on and so forth. And we get these 4 values. Now, with these values, ideally with a titration, at least 3 values need to be within 0.1 of each other. Okay, so 0.1 mils. Generally, the first one as well is also a rough value. It's usually an outlier. We use that as basically a speed run to save time. We know, okay, well, the endpoint's going to be at about 24.55, so we'll go quickly to about 23 and then go slowly. Okay, so generally what we do with that rough titration, so we call it a rough titer or an overshoot titration, we usually exclude that one. Okay, unless it's in agreement with your other ones, unless you're that good that they're all in agreement, by all means keep it. But generally it will be out. Okay, so what we do is we exclude that one. We also exclude any other major outliers. So certain things can happen. You might not wash out your conical flask well enough, or a drop might come out of your volumetric pipette if you jostle it around too much, or any other kind of inaccuracies can happen. So we generally want to find at least 3 values within that 0.1 range. If there's outliers, we exclude them. Okay. Generally, some other weird things can happen. Like I've had in the past students do 6 titrations and 3 will agree and another 3 will agree. And so they have to pick between them. So I just get them to do another one and see which one it agrees with. So yeah, there's lots of fringe cases, but generally most of them will be within 0.1 mil if you're doing the right thing. Okay, so we take our average, so we just take the mean of the 3 values that are close to each other, which gives us a mean value of 24.10 milliliters. Okay, and we're going to use that in our calculations as a blue square with VNaOH of being 24.10 mils. So that's the first thing. We find out our volume from our titrations. Now, to determine the concentration, so that was our question. Let's go through it and let's find out the important stuff. So you know what I like to do. You know I like you to highlight numbers, units, special phrases. Okay, and for chem, also the actual chemical that we're using. So to determine the concentration of sample of sodium hydroxide is titrated against 25 mil samples of 0.1059 molar hydrochloric acid. So that tells us 2 things. It tells us the volume of HCl, which is 25 mils, and it also tells us the concentration of HCl, which is 0.1059 moles per liter. We know the volume of NaOH from our previous calculations, from our titers, 24.10 mils. And it's asked us to calculate the concentration of the sodium hydroxide. So our CNaOH is our question mark. It's going to come out in moles per liter. Now, how do we do it? This is how we do it. This is a flow chart. If you're good with flow charts, we use volume and concentration of our first reagent that's known to calculate the number of moles of the reagent that's known. We then use our mole ratio to calculate the number of moles of reagent that we should have at equilibrium, not at equilibrium, at equivalence. Okay. We can then use the volume of the reagent and the number of moles to calculate the concentration of our second reagent. Okay, so this is our flow chart. This is the same for every titration calculation question around. Okay, there might be extra steps, including masses or stuff like that. Or other things like dilutions, but this is the basic thing. We use volume and concentration to calculate the number of moles to calculate number of moles through mole ratio, the number of moles and volume to calculate concentration. Okay, commit that to memory. So what do? How does that look? So we write out our equation. NaOH plus HCl gives us salt and water. In this case, it's actually just table salt and water. Nice and easy. Check that it's balanced. So there's one sodium on the left, one sodium on the right, one oxygen on the left, one oxygen on the right, two hydrogens on the left, two hydrogens on the right, one chlorine, one chlorine. Good, balance, done. Mole ratio then is 1 to 1. So it's going to make it easier for our calculations. That's what we want from that part. We need to write the equation. Always remember your states. Balance it. And then we need that mole ratio, so it's 1 to 1. So, number of moles of HCl, concentration times volume. So remember, C equals N over V, so therefore N equals C times V. So NHCl is 0.1059 times 0.025. Number of moles of HCl is 2.648 times 10 to the negative 3. Now, mole ratio, 1 to 1. Nice and easy. That means that the number of moles of sodium hydroxide is equal to the number of moles of hydrochloric acid. So it's 2.648 by 10 to the minus 3 moles. Now, to calculate the concentration of our sodium hydroxide, it's the number of moles divided by the volume. So C equals N over V. Number of moles we calculated just then. Okay, it's that bluey indigo weird color box over our nice blue box, which was our volume of sodium hydroxide that we calculated from the titer tables, is 0.02410. So we end up with 0.1099 moles per liter. Okay. Now, I haven't done it in this this slideshow, but you have to remember the sig-fig rules. Okay. Sig-fig rules, the lowest number of significant figures, that should be what your answer's in. If you go back and have a look at this, you can actually kind of see that it's the 25 mils was just given as 25 mils. It wasn't given as 25.0 or 25.00. It was just 25 mils. So realistically, this answer should be in two significant figures. So it should be 0.11 moles per liter as our answer. Now, just remember, in our HSC, there's typically up to 1 mark is given for sig-figs. Okay, we don't multiple penalize you for it. There will be one question and you get 1 mark for it. Typically it is a titration question because it is about accuracy, okay, and precision. So it will typically be that. But if you see other things with like 3 or 4 sig-figs, just remember the lowest number of sig-figs is what our answer should be in. Okay. And while it might not be necessarily giving you extra marks, don't forget that the HSC raw mark doesn't always equal your HSC exam mark. Okay, we look at things like our course descriptors. So what is a band 6 answer? If this person is giving all of your answers as with the proper sig-fig rules, that pushes it more towards a band 6 than a band 5, or more towards a band 5 than a band 4. So if you're kind of on the cusp, then it'll push you more towards the higher band. Like for example, I had 2 students this year who had 79 as their exam mark. Okay, both of those students must have just not been good enough for a band 5. So they deserved a band 4, but the highest band 4 that they could get. It wasn't quite there, but if they'd have done something like this, put in more of the sig-figs rules, they probably would have done better. Okay, let's get on to sample 2. To determine the concentration of a sample of sulfuric acid, 25 ml samples of it were titrated against 0.2354 molar sodium hydroxide. The burette readings are shown below. What is the concentration of the sulfuric acid solution? So here we've got some initial burette readings. I've made all of them non-zero so that you actually have to do maths. So remember, first things first, doing our titers, final, take away initial, okay, and then calculate, look for any outliers, then calculate the average. So here we have 28.75, 28.6, 28.65, 28.6. Okay. Notice how the top one is 0.15 above the lowest one. Okay. So that one's going to be cast as an outlier. And it's the first one, so it's just a typical overshoot titration. But whoever did it got it pretty close. Okay. So 28.6, 28.65, 28.6, average them out, gives us 28.62. Okay. Sorry, I've also, because all of the inputs are 2 decimal places, I'll just put the answers as 2 decimal places here as well. Just because that helps us with our sig figs rules. So 28.62, that's our volume of sodium hydroxide. Now, let's go through, highlight the important stuff. What is it? 25 ml samples of sulfuric acid were titrated against 0.2354 mole of sodium hydroxide. What is the concentration of our sulfuric acid? So, 25 ml samples of sulfuric acid, so we have volume of H2SO4 is 25 mils. 0.2354 molar sodium hydroxide is our concentration of sodium hydroxide. Volume of sodium hydroxide, 28.62 mils, that's from our titer table. And we're asked to calculate the concentration of sulfuric acid, so that's our question mark. So CH2SO4 is our question mark. Remembering our flowchart, okay? Volume times concentration to give us number of moles. Number of moles, we calculate that through mole ratio, which is going to be important for this one. And then we use N and V to calculate C. So, firstly, sodium hydroxide plus H2SO4, what does that give? Well, acid plus base gives us salt plus water. The salt will be sodium sulfate and water. Now, go through. Is it balanced? 1 sodium, 2 sodiums. Immediately, no, it's not balanced. Okay, so we have to balance it. How do we balance it? Well, we add another sodium. Okay, that will give us 2 sodiums, 2 oxygens. Sorry, 6 oxygens. So we also have to balance out the water on the other side. Okay, if you can't remember how to balance, come and see me, or send me an email. I'll help you balance. I've got so many balancing equations questions. It's super important for the HSC, so make sure you've got that down pat. Now, mole ratio is 2 to 1. So 2 sodium hydroxides for every sulfuric acid. That's going to be important in our calculations coming up. Firstly, following our flowchart, calculate number of moles of sodium hydroxide through concentration and volume. So we have concentration and volume, multiply them together, we get that. So number of moles of sodium hydroxide is 6.737 times 10 to the negative 3. Okay. We then calculate the number of moles of H2SO4 through our mole ratio. Okay, so it's 2 to 1. So the number of moles of sodium hydroxide will be double the number of moles of H2SO4. Because for every 2 moles of sodium hydroxide that react, 1 mole of sulfuric acid will react. Okay, so that's how we do that. So number of moles of sodium hydroxide is 2 times the number of moles of H2SO4. So therefore, the number of moles of H2SO4 is half of our sodium hydroxide value. So 6.737 times 10 to the minus 3, divide that by 2, gives us 3.369 times 10 to the minus 3 moles of sulfuric acid. We then calculate the concentration of that. So number of moles divided by the volume. So 3.369 by 10 to the negative 3 over 0.025, so 25 mils, is 0.1347 moles per liter. Okay. Now again, we were just given 25 mils for our volume of H2SO4. So our sig fig rules, we really should round that to 0.13 moles per liter. Okay. But again, just here, I haven't done it. We're mainly looking at the calculations today. But yeah, if you want those higher band answers, remember your sig fig rules. Okay, that's it for today. No summary, just go straight on, do the examples, do the questions, and let me know if you need any help. Thank you.